Section 3, we're introduced to the equilibrium constant. This is a big deal. The section itself is not very big or very long, and I think you'll understand it pretty quickly. Nevertheless, it's really important. Okay, so the equilibrium constant is going to be written in terms of K. We're going to do equilibrium constant in chapter 15 and in chapter 14 and in chapter 15 and in chapter 16. So it's really 3 chapters worth of concepts right here. And K is going to be written as the ratio of the products over, what am I talking about? The reactants. Okay? Alright, so let's get more specific now. Suppose we had some reaction, which we're going to describe here as A, B, C, and D, okay? And suppose we have A moles of A moles of A, B moles of B, C moles of this stuff over here, and guess how many moles of D we have, right? Good. Okay, so the law of mass action is where we get our expression for K. The law of mass action says that the ratio of these guys, that is the products over the reactants, is going to be constant at a particular temperature at, here, big deal here, at equilibrium. Okay? So that is, I mean, you could always start some reaction out. You've got a bucket here, right? And you have nothing in it except A, right? In which case, this ratio would not exist, right? But if you have A and B in here, and you give it enough time, such that it has time to produce C and D, right, then this ratio will be true. Okay, so again, that's at equilibrium at a particular temperature. This ratio will be constant. All right, so let's look at how we can use this and how we can manipulate it. Suppose that you were asked to express the equilibrium constant for the chemical equation, such and such. Okay, look at this. Now the law of mass action says that K is going to be the concentration of the products over the concentration of the reactants, right? And the products are here. So it's going to be H2. Sorry for the background noise there. I'm not working alone. Over carbon monoxide, right? Over methanol. Okay? One thing I haven't written yet is that. And remember what we do with that? That goes right here. Okay? So that's it. That is the equilibrium constant expression for this reaction. And that's the answer. Alright, so let's think about what that means. I've already described it a little bit. Let's look at some pictures which help us appreciate that. Alright? So suppose that we have some reaction, H2 and Br2, and they're in equilibrium with each other. And what that means is that we get some of this that goes to that, right? And also some of that goes back and forth. That's what that means. That's what these arrows mean. Big time, big deal, by the way. This is not the same thing as that. And it's not the same thing as that. And it's not the same thing as that, okay? These mean different things. So we need this when we're talking about some reaction that's going back and forth, okay? So some of these are going to combine to form these, and some of these are going to combine to form those. And that's what this means. Now, suppose that K is a large number. If K is a really large number, what does that mean? That means it's mostly HBr. Okay? Now, if it's a really large, let's suppose that this was all 1 liter and each one of these represented 1 mole. Let's calculate what this would be. This would be, so this is HBr over here, right? 1, 2, 3, 4. We're going to say the volume is 1 mole. Or rather, volume is 1 liter, and each one of these represents a mole. What would the concentration of HBr be, hydrobromic acid? Pleasure. This is not so important. Please hold off on that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the concentration of hydrobromic acid would be, just a second here. Pleasure?
Yes.
You can do some of that stuff over there. Just think it's going to cause a lot of noise.
Yes.
Okay, the concentration of HBr, if there was 9 of these, and each one of them represents a mole, would be 9, and we're in 1 liter, right? Moles per liter, which is 9 molar, okay? And what is the concentration of H2? Well, there's only one of them in here, right? So the concentration of H2 is 1 molar. And can you see what the concentration of, can you see the bromine here? Concentration of bromine is equal to 1 molar. Also, there's only one of them, right? So what is K? K is equal to HBr, which is 9. Rather, we're going to put this in parentheses, squared, times 1 times 1, which is 81, which is a large number. I would say oftentimes we're going to find the numbers are much larger than that. But can you see what I've got there? The equilibrium constant would be 81, and that would mean that we have mostly HBRs. Let's consider another possibility. Suppose that K is a small number for a particular reaction. What does that mean? All right, so let's take this here. Let's take this here and say that we've got 2, and let's let this volume be 1 liter again, okay? 1 liter. And 1 liter, and we've got 2 of these here, right? So the concentration of NO, can you see this is NO, right? This is an NO. It looks like it's 2 molar. We're letting each of these represent 1 mole. All right, what's the concentration of O2? Concentration of O2, looks like there's 1, 2, 3, 4. 4 molar, and the concentration of N2 is 1, 2, 3, 4, 5, 6. 6 molar. Okay, if this is true, or rather, if this is at equilibrium, then K is going to equal NO2 squared over 4 times 6, which is equal to 4 over 24, which is equal to 1/6, which is approximately equal to 0.167. Okay? And so that's a relatively small number. Can you see that that's between 0 and 1? So that a small number means that the products are mostly not going to predominate. This is what's going to predominate, right? If you have a big denominator, that gives you a small number. Okay, so that's what that means. This brings us then to a key result. Key result, if K is much smaller than 1, you should write this down. You should pause the video here at this point and say what that means. If K is much smaller than 1, what does that mean? Okay. Let me suppose you pause it, and this means that if K is much smaller than 1, this means we have a big denominator. Which in turn means reactants predominate. What if K is equal to 1? That means the numerator is equal to the denominator. Right? And that means that the reactants are about the same as the products. It's going to be about 50-50. Okay? And what if K is really big? That means we have a big numerator. Which means the products predominate. Okay? And I think the last thing I'm going to ask you is, let's just apply this. I think we've got an example coming up next. Let's apply this. So let me go to blue. Suppose we have some reaction which goes like this: A to B, and let's suppose that A basically disappears. Like there's no A here, okay, at equilibrium. What is K? A basically disappears at equilibrium. In other words, it almost entirely goes to B. What is K? Okay, K would be very, very big. And let's say if it really disappears, it would go to infinity, right? But if it basically disappears, this is going to be a very large number. Let's say 1 times 10 to the 40, you know, or 50 or whatever, okay? Which is a big number. Not infinity, but a big number. All right, so that's what we mean by K. Now let's look at how we can manipulate K. So suppose that you're given some reaction, and you'll be asked to do this on an exam. It's really it's a really common trick that we need to utilize, and frankly, I think you're going to find it's easy. So suppose you're given some K, and the K that you're given, let me go back to red here. My primary color is red. Let me go back here and say, suppose this is what you're given. If you're given that, calculate the equilibrium constant for the following reaction. These are always going to be basically the same thing. Can you see that over here, I've got NH3 as a product. Here it's a reactant, right? So if K looks like I misspelled that. It's products over reactants, then this K is going to be switched, right? We're going to switch these guys, boom and boom. If we're going from over here, it's a product, and here it's a reactant. So from here to here, the first thing I'm going to do is I'm going to say K prime, or rather, you know what I'm going to do? I'm going to take this reaction, and I'm going to turn it around and make it negative, okay? Or, you know what, we're doing this by exponents, so I'm going to say K to K prime. First thing I'm going to do, okay, where this, let me go, watch this. Blue, this is N2 plus 3H2 produces 2NH3 as this one. This one now is going to be 2NH3. Oops, that's an equilibrium with. Ooh, I broke my own rule there, didn't I? Is an equilibrium with. See how I switched it around? N2 plus 3H2. Do you see that? That's this one. Oops, that's that one there. Okay? But that's not what I have here. Okay? So this K all right, so let's manipulate this thing. Let me go back to my favorite color, red. All right, and we're going to say K is this. So now watch this. K of this guy, consider the chemical equation, an equilibrium constant for the synthesis of ammonia. Very common reaction. We use it a lot in examples. Nitrogen plus hydrogen gives ammonia. Okay, and that gives us that. Well, the K for that reaction, 3.7 times 10 to the 8th, watch this now, is ammonia, the concentration of ammonia squared, right, because there's a 2 here, over the concentration of nitrogen times the concentration of hydrogen cubed, right? And we know what that number is. It's this. 3.7 times 10 to the 8th, okay? Now let's look at this other one. This other one, K prime, we don't know what the number is, but we can express it, right? We can say that is equal to H2 to the 3/2 times N2 to the 1/2 over NH3. All right, so there's two differences between these two, and I don't know what this is. That's really what we're asking, right? There's two differences between these two. One of them is that this is upside down, right? The NH3 is on the bottom over here, it's on the top over here, okay? So let's say for K, let's go back to red now. For K, if we take this and make it upside down, 1 over K, that's going to equal N2 H2 cubed over NH3 squared, right? Do you agree with me? You see what I did there? I flipped it. I inverted it. And now that looks more like that, right? Now can you see that if I square K prime, I'm going to get that. Oops, that's backwards. There's N2 and there's N2. There's H2 and there's H2. Okay? But if I take the square root of this, that's going to equal to, I'm going to switch this back around. Do you mind? Because it doesn't matter, of course, what order I do those in. 3 times 1/2, 3/2. Oh, I can't just do the one side. I got to do both sides, right? See that, to make it equal, to make it a true statement? N2, and that was 1/2 over NH3, and then 1/2 times 2. So or rather I should say squared raised to the 1/2, square root of the square, of course, is just that. Agreed? Do you see that? And this is K prime. So it looks like K prime is, see, these two are equal to each other now. This is equal to that, which is equal to that. It looks like it's 1 over, it's the square root of 1 over K. So it's going to be the square root of 1 over 3.7 times 10 to the 8th. You see that? Okay. I'm going to put my calculator out now. And I'm going to say, I'm going to put mine in parentheses first. 3.7 times 10 to the 8th raised to the minus 1/2. Okay, and so I get 5.20 times 10 to the minus 5. All right, that's what K prime is. 5.20 times 10 to the minus 5. Let me just check my notes here, make sure I don't make any mistakes. It's very frustrating when you do. Actually, I'm not even going to check the notes. I want you to walk through this with me. So first of all, let's just go backwards now. Let's take this and square it. 5.2 times 10 to the 5.2 times 10 to the minus 5 squared. Okay, and then we're going to 1 over that. Okay, or 1 over that. Let me see. Well, that's right. Okay, so what I did to check this is I took this and I squared it. and then I inverted, right, which is 1 over x. That's your 1 over x key, and this is your x squared key, right? And that's the opposite of what I did here. And sure enough, I got 3.69822 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8, which is that. Okay? All right, so very good. Let's stop this here. You ask questions if you want to see more examples. Good luck.